Hi guys, this is the EdExcel AS level further maths paper 2 covering the decision 1 section. So let's get straight into it. Question 1. We have figure 1 over here, which represents a network of pipes in a building, and the number on each arc is the length in meters of the corresponding pipe. We have to use Dijkstra's algorithm to find the shortest path from A to F, and we have to state the path and its length. Okay, so we have this over here, this figure. We've got the vertex. Those are labelled A to G. We've got the order of labelling in the second box, and then we've got the final values, and in the bottom box we have the working value. Now, if you remember from the question, we want to start at A and finish at F. So if we start at A, of course, we begin with a 0, and then we take this value into this box and we label A with a number 1. So from A to B, C and D, A to B, that's 13, A to C, that's 27, A to D, that's 37. Okay, and you'd find the smallest number to be 13, and therefore we have B2, the value that we take in is this 13. Now 13 plus 7, that's 20, and 13 plus 12, that's 25. Now the smallest of all these is the 20, so we take this 20 inside here, and then we label E with a number 3. 20 plus 4, that's 24. And now you'd find the smallest one to be this 24. So we take the 24 inside here, we label C with a number 4. Now 24 plus 35, that's 59. 24 plus 23, that's 47. 24 plus 10, you'd find that to be 34. The smallest one, you'd find that to be 34. So we take 34 inside here and we label D with a number 5. 34 plus 11, that's 45. And of all of the remaining boxes, 45 is the smallest one. So we take 45 in here and we label G with a 6. Now 45 plus 10, that's 55. So 55 is the smallest. We take this inside here and then we label F with 7. And therefore, in terms of the shortest path, we want to end up at F. So if we work backwards from F, 55 take away 10, that's 45. 45 take away 11, that's 34. 34 take away 10, that's 24. 24 take away 4, that's 20. 20 take away 7, that's 7. 13 take away 13, that's 0. So therefore, in terms of our shortest path, we have A, B, E, C, D, G, and F. So this is our shortest path, and in terms of the length of the shortest path, you'd find that to be 55. Okay, so we have 55 as the length of the shortest path. And now for part B, on a particular day, Gabriel needs to check each pipe, a route of minimum length which traverses each pipe at least once and which starts and finishes at A needs to be found. We have to use an appropriate algorithm to find the pipes that will need to be traversed twice. You must make a method and working clear. Well, of course, in this question, we would have to use the Chinese Postman algorithm. Now, with the Chinese Postman, the first thing you want to do is label the odd vertices. So in terms of the odd vertices, you'd find we have A, that has order 3, B, that has order 3, D, that has order 3, and G, that also has order 3. So let's just write those odd vertices down. For the odd vertices, we have A, B, D, and G. And the next thing we need to do is write down the pairs and their corresponding smallest lengths. So we have AB, and then we also have DG, and then we have AD with BG, and then we have AG with BD. Those are our pairs, and if we work out the smallest length A to B, you'd find that to be 13, and DG, smallest length, that's 11. And if we consider AD, well, AD, we can either take this 37, that's one way, or a smaller way to start at A and finish at D. We can go A to B, which is 13, then we can go B to E, that's 7, and then we can go E to C, that's 4, and then we can go C to D, that's 10, and if we work out this total, you'd find we get 34. So of course we write down the 34 instead. Okay, let's just get rid of this. In terms of BG, starting at B, finishing at G, the smallest way we can get there, well, we start at B, and then we can go B to E, that's 7, and then we can go E to C, that's 4, and then C to D, that's 10, and then D to G, that's 11. So working all this out, we get 32. So the smallest length from B to G, that's 32. Okay, and in terms of AG, starting at A, finishing at G, now we can go 37 plus 11, which is 48. Alternatively, we can go A to B, that's 13, and then B to E, that's 7, and then E to C, that's 4, and then C to D, that's 10, and then D to G, that's 11. And if we work this out, you'd find we get 45. So we write down 45 here. Okay. Now, in terms of B to D, starting at B, finishing at D, we can go 12 plus 10, which is 22. Alternatively, we can go B to E, which is 7, and then E to C, which is 4, and then C to D, which is 10. You'd find this to be 21. So 21 is the smallest one. Okay, so those are our pairs. And what you'd find then is, if we add these up, we have 24, 66, and 66. This 24 is the smallest, so therefore we would have to repeat AB and also repeat DG. So we have to repeat AB, that has length 13, and DG, that has length 11. Okay? And therefore, if we go back to the question, the pipes that need to be transversed twice, those will be AB and DG. And in terms of part C, we have to find the minimum length. Well, we have this total weight of 189, and then we add on this 24 over here, and therefore you'd find the minimum length to be 213 meters. Now for part D, a new pipe BG is added to the network. A route of minimum length that traverses each pipe including BG needs to be found. The route must start and finish at A. Gabriel works out the addition of the new pipe increases the length by the route by twice the length of BG. We have to calculate the length of BG. You must show you're working. So I think at this point it would be a good idea to once again insert this diagram, and we don't know the length of BG. Let's just call that X for now. Okay, so there's a route directly taking us from B to G of length X. And in terms of the odd vertices, in terms of what's odd, A is odd, and also D is odd. There is nothing else which is odd. So A and D are odd. And therefore we know A and D, if we go back to what we found here, that was 34. So AD equals 34. Now, therefore, the minimum time to traverse all paths, let's just write this down. The minimum time to traverse all paths, we have this 189. Now BG, instead of it being 32, it is now X. Okay, so that refers to this over here, this X over here. So we have 189 plus this X plus this 34. Okay, and we were also told in the question that Gabriel works out the addition of the new pipe increases the length of the route by twice the length of BG. So we've got this length of the new root. We have 213 plus twice bg. So we have 213 plus 2x. So if I grab a different color highlighter, this over here came from this statement over here. And we set this equal to this over here. So this is equal to 189 plus x plus 34. And therefore you'd find x to equal 10, of course. Bg, that is equal to 10 meters. Question number 2. We have this figure 2 over here, and a teacher buys pens and pencils, and the number of pens x and the number of pencils y that he buys can be represented by a linear programming problem as shown in figure 2, which models the following constraints. We have 8x plus 3y being less than or equal to 480, 8x plus 7y being greater or equal to 560, y being greater than 4x, and x and y being greater than 0. The total cost in pence of buying the pens and pencils is given by C equals 12x plus 15y. We have to determine the number of pens and the number of pencils which should be bought in order to minimize the total cost. You should make a method and working clear. So I've just written out those inequalities now. When x is 0, for the first inequality y is 160. That corresponds to this line over here. We'll just add that in. So we have 8x plus 3y equals 480. When x is 0, y is 80. That would correspond to this line over here. So we have 8x plus 7y equals 480. Here of course we have the y equals 4x. Okay, so that's then 3 done. And essentially one of the ways we can solve this is to either draw the objective function, alternatively we can test each of these 4 points of intersection. Now this point of course is 0, 80. Here we have 0, 160. Here we can read off we have 24, 96, and for this point we have to be a bit careful. We have to solve this equation with this equation simultaneously. So if we solve this equation with this equation simultaneously, so let's just write that down. Solving equation 1 and 2 simultaneously, we have, if we replace this y with 4x, we have 8x plus 7 lots of 4x equals 480. So we have 28 plus 8, that's 36, so we have 36x equals 480. Of course you'd find x to equal 140 over 9. Okay, and therefore y is equal to 560 over 9. So therefore this point of intersection you'd find to be 140 over 9 and 560 over 9. Okay, and what we can now do is we can test each of these points by substituting them into this function over here to see which gives us the minimum. So let's continue doing that. When we have x equals 0, y equals 160, c is equal to 12 times by 0 plus 15 times by 160, which is 2400. When x is 0, y equals 80, c equals 12 lots of 0 plus 15 lots of 80. You'd find this to be 1200. When x is equal to 24, y equals 96, we have c, which is equal to 12 lots of 24 plus 15 lots of 96. You'd find this to be 1728. And when x is equal to 140 over 9 and y is equal to 560 over 9, c is equal to 12 lots of 140 over 9 plus 15 lots of 560 over 9, which is 1120. The smallest one, obviously, that's this one. And therefore, in terms of integer coordinates, you'd find the integer coordinates to be 1663, and therefore you'd find we need to buy 16 pens and 63 pencils. Question number 3. We've got this table over here which shows the activities required for the completion of a building project. For each activity, the table shows the time taken in days to complete the activity and the immediately preceding activities. Each activity requires one worker. The project is to be completed in the shortest possible time. We have to draw the activity network described in the table using activity on arc. Your activity network must contain the minimum number of dummies only. Okay. I think this question requires a fair bit of thinking. So I think if we take this slowly, hopefully, we should be able to get through it. So I've just copied the table into the answer book, and remember the definition of a dummy. We require a dummy when we have at most one activity between two events. Now, if you look at A, B and C, they depend on nothing. So we have A, B and C. Okay. Now, I recommend ticking off as you go along. If you look at activity D, that depends on A and B. So once A is completed, we can do activity D. And we can't go like this from A to B, from A to D like that. Instead, we'd have to have a dummy. Because remember, we have at most one activity between two events. So we have a dummy over here. So that's D done. If we take a look at E, that depends on D. So we have E over here. If we take a look at activity F, that depends on B. So let's just say F goes over here. That's F completed. And if we look at G, that also depends on B. So let's have G coming out over here. And if you look at H and I, those depend on C and G. So for us to do activity H, C and G need to be completed. So we have this situation going on. So that's H. And activity I, that also depends on C and G. Like that. Now, essentially they must all finish at some common point. So this finishes here, if that makes sense. Same with F, that finishes somewhere here. H finishes here, and so does I. But remember, with I, we can't have more than one activity between two networks, two nodes. So instead, for I, we would have to have a dummy instead. Okay? So we'd have to have a dummy instead, like that. Okay? So that is the activity network completed, and I'll just draw this out neatly. So I've just drawn it out neatly, and let's also add in the time taken as well. Let's just tidy all this up. The time taken for A we have 5, B we have 7, C we have 3, D we have 4, E, whatever that is, we have 4, F we have 2, G, which was this one, we had 4, H we have 5, and I we have 10. Of course, for these dummies we'd have 0 and 0. Okay, so that's that completed. And now for part B, we have to show that the project can be completed in 21 days, and then we have to identify the critical activities. Okay, so I think for this we have to draw a proper diagram. So let's work through this. Let's do the forward passes and the backward passes. Forward passes we'll do at the top. We start off with 0, and then we have 5 going this way, and then we have over here what goes into B is 7, and then what goes over here is 3, and then from the 7 we can add 4 to get 11. So 11 is the bigger one, so we put 11 inside here. Okay, so let's just get rid of this. So we put 11 inside, like so. And 7 plus 0, that's 7. So we have 7 here. 7 plus 4, that's 11. 11 goes in here. 11 plus 4, that's 15. 7 plus 2, that's 9. And what else goes in? 11 plus 5, that's 11 plus 5 is 16. And then 11 plus 10, that's 21. And then 21 plus 0, that's 21. 21 is the biggest one, so 21 goes inside here. And that's all the forward passes done. Now let's do the backward passes. We'll do these in blue. 21 take away 0, well, let's put 21 here. 21 take away 0, that's 21. 21 take away 10, that's 21 take away 10, that's 11. 21 take away 5, that's 16. 21 take away 2, that's 21 take away 2, that's 19. 21 take away 4, that's 17. 17 take away 4, that's 13. 13 take away 0, that's also 13. And well, obviously here we choose the 11, it's the smaller one. 11 take away 4, that's 7. 7's the smaller one, so we put that in, and then the smaller one obviously will always go back to 0. So hopefully you should all be familiar with that by now. Let's rub this out. So in terms of the critical activities, well, what we see over here then is indeed it does take 21 days to complete. So let's just write that down. So the numbers at the end of activity E indicate that the project can be completed in 21 days. Okay, so that makes sense. And in terms of the critical activities, what's critical, if we highlight them, we have B, and then we have B, G, and then G to I. Okay. And then obviously back up the dummy as well. So in terms of the critical activities, let's just write this down. In terms of the critical activities, we have B, G, and I. Let's just highlight that. Okay, so that's the end of this question. Question 4. We have to explain why it's not possible to draw a graph with exactly 5 nodes with order 1, 3, 4, 4, and 5. And to do this question, of course, we would have to make use of the handshaking lemma, in which we know that the sum of all the orders of vertices of any graph is twice the number of arcs. Okay, let's just use that for now. So we've got that definition down of the handshaking lemma. Of course, the sum of all the orders of vertices of any graph is twice the number of arcs. So the number of arcs, if we find out the total of the sum of the orders, we have 1 plus 3 plus 4 plus 4 plus 5, and if we then divide that by 2, that tells us the numbers of arcs. So we have 1 plus 3 plus 4 plus 4 plus 5, and if we divide this by 2, you'd find that this is 8.5. And 8.5, of course, 8.5 is not a integer, and therefore what we can conclude from here is that a graph cannot contain an odd number of odd nodes. Okay, and we have that over here. We have 5. We have 3 odd nodes. Okay, and we can't have that. So that's part A done. For part B, a connected graph has exactly 5 nodes and contains 18 arcs. The orders of all the 5 nodes are 2 to the power of 2x minus 1, 2 to the power of x, x plus 1, 2 to the power of x plus 1 minus 3, and 11 minus x. We have to calculate x for the first part of part B. Well, again, using this handshaking lemma, if we add up all the orders and set that equal to twice of the number of arcs we were told that was 18. So we were told that we have 18 arcs. If we work that out, so adding them together, we have 2 to the power of 2x minus 1 plus 2 to the power of x plus x plus 1 plus 2 to the power of x plus 1 minus 3 plus 11 minus x. This is equal to twice of 18, and the reason we have twice of 18, we have 18 arcs, and we're using this handshaking lemma. Okay, so we can tidy all this up a bit. You'd find over here, if we tidy this up, well, first of all we have plus x minus x, 2 times by 18, well, also minus 1 and plus 1 cancel. Now 11 minus 3, that's 8, and then 2 times by 18, then minus the 8, that's 28, and if we take that over to the other side, we have minus 28. And what else do we have? We have 2 to the power of 2x, and then we have 2 to the power of x. Let's just add that on, 2 to the power of x. And then here we have 2 to the power of x times by 2. Okay, and then we have this minus 28, and this is equal to 0. So here you'd find we have 3 lots of 2 to the power of x. And here we have 2 to the power of 2x, and then we have minus 28, and this is equal to 0. I'll just move this over here. Now this is a disguised quadratic which we can factorize. Of course, let's just write that down. We have a disguised quadratic, and hopefully you should have met disguised quadratics in your regular A-level maths. We can factorize that as 2 to the power of x plus 7, lots of 2 to the power of x minus 4, and this is equal to 0. Of course, from here, 2 to the power of x cannot equal minus 7, because remember, we can't take, when we use the laws of logs, we can't solve this. From here, we have 2 to the power of x equaling 4, and therefore the only solution, x is equal to 2. For the next part of part B, we have to state whether the graph is Eulerian, semi-Eulerian, or neither. You must justify your answer. Well, if we work out what the nodes are, knowing that x is equal to 2, we have 2 to the power of 2x, so we have 2 to the power of 4 minus 1, which is 15. Okay? And then here we have 2 to the power of 2, which is 4. And then here we have 2 plus 1, which is 3. Here we have 2 to the power of 2 plus 1, then minus 3, that's 5. And then 11 minus 2, that's 9. And then what you'd see over here is that there are more than 2 odd nodes. Let's just write this down. There's more than 2 odd nodes. And because of that, we can conclude that the graph is neither Eulerian or semi-Eulerian. Oh, let's just write that down. The graph is neither Eulerian or semi-Eulerian. Now for part C, we have to draw a graph which satisfies all of the following conditions. So the graph has exactly 5 nodes. Let's just draw the 5 nodes on. So we have 1, 2, 3, 4, 5. That's 5 nodes. The graph is not Eulerian. Okay, so now by definition, what we mean by Eulerian is the graph is connected and all the vertices are even. So these are the 2 conditions which must be satisfied for an Eulerian graph. Now we were told that the graph is not Eulerian. Okay, and also with an Eulerian graph, one thing about an Eulerian graph is that it starts and ends at the same, starts and finishes at the same vertex. So we can probably guess from here that the graph is not connected. Now, if the nodes have orders 2, 2, 4, 4, 4, let's write down those orders 2, 2, 4, 4, 4. One thing that we can do is, well, if we connect this graph, this node to this node, you'd find the order here is 2 and the order here is 2. And with these remaining 3, we want the orders to be 4. Well, if we connect this to this, this to this, and this to this, so far you can see that here we have 2, 2, 2, but instead we want 4, 4, 4. So what we can do is instead, if I connect this to this, and then this to this, and then this to this, you'd then find, instead of us having this 2, and this 2, now we've got 4, 4, 4, and the graph is not connected, and I can't start and end at the same vertex. Okay, so this satisfies the conditions required. Okay, so that was a bit tricky, I think, but I think the idea over here is to know your definitions of what an Eulerian graph is and what the definition of a semi-Eulerian graph is, and I think if you know that, I think it'll be in a good position. So I think with this question was quite good in making sure you understand the definitions of what a graph is. Question number 5. Jonathan makes 2 types of information pack for an event. We have standard and value, and each standard pack contains 25 posters and 500 flyers, and each value pack contains 15 posters and 800 flyers. He must use at least 150,000 flyers, and between 35% and 65% of the packs must be standard packs, and posters cost 20p each and flyers cost 4p each. Jonathan wishes to minimize his costs. Let X and Y represent the number of standard packs and value packs produced respectively. We have to formulate this as a linear programming problem, stating the objective and listing the constraints as simplified inequalities with integer coefficients. Okay, so I think one of the more accurate ways to approach this is to first of all draw a table. Okay, so we've got posters and flyers. Let's just write this down. We have poster and flyer, and then we have standard and value. So we have standard, which is X, and value, which is Y. Okay, so we have value, which is Y. I think that's the first thing we can do. And if we were to state the number of X and Y we have for poster and flyer, that's quite easy to do as well. If you go back to the question, we have standard, which contains 25 posters and 500 flyers, so we have 25 and 500, and we were also told that we have for value 15 posters and 800 flyers, so we have 15 and 800. Okay, now we were also told that he must use at least 150,000 flyers. So the total over here for flyer, let's also add this in. We have 150,000. Okay. Now the first thing to notice, if we have at least 150,000, we can form our first inequality. 500x plus 800y being greater or equal to 150,000. And therefore, if we divide through by 100, you'd find 5x plus 8y to be greater or equal to 1500. Okay, that's the first thing to notice. And the second thing to notice is, in terms of the cost, we have posters which cost 20p each and flyers which cost 4p each. So in terms of posters, in terms of the cost, let's just create a new, actually we'll do it separately like this. In terms of the cost, it's 20p for a poster. So if it's 20p per poster, we have 20p, which we'll write as 0.2, converting it into pounds. And then we have 25 standard posters, so we have 25x plus 15y. And then we have 4p for flyers, so we have 0.04 lots of 500x plus 800y. And therefore, you'd find the cost to be 25x plus 35y. Okay, so that's just collecting like terms. And what else we can do over here? If we go back to the question, we were told between 35% and 65% of the packs must be standard packs. So somewhere we'd have this sort of inequality. Standard remembers x. Now we have between 35% and 65% of packs. So that suggests to us that we have 35% of the total x and y, and 65% x and x plus y. So we have the 7/20 lots of x plus y being less than or equal to x being less than or equal to 13/20 lots of x plus y. So if we multiply through by 20, we have 7x plus 7y being less than or equal to x being less than or equal to, well, we have 20x being less than or equal to 13x plus 13y. And if we split these inequalities into two separate parts, if we first of all split the inequality like this, taking 7x from both sides, you'd see that 7y is less than or equal to 13x. And then if we split the other one like this, taking 13x from both sides, you'd find 7x is less than or equal to 13y. So we have two inequalities as shown. And that's basically it. We've got this inequality, this inequality, this inequality subject to this, and we also have x and y both being greater or equal to 0.